Welcome back. Uh, so we'll continue our discussion on this fundamentals of fluid mechanics. So if we connect back from our last session, so where we're talking about the intensive and extensive properties. So obviously, I mean, just to recall that extensive properties are the one which is very much, I mean, include the mass, vary with the amount of the substance. So that is what the extensive properties are. Whereas so obviously one can think about mass, weight, volume, whereas in the intensive properties do not depend on the amount of the substance. So now what we talk about today, we are talking about the system which might change in volume with time. And then from there, we try to kind of derive those equations from the control volume system. Now, here, if you look at it, you have a moving system. So the system is moving from here to here to here. So which may change its volume and shape. And that is happening. If you see the situation here, you see the situation here, and you see the situation here. So the system here, it's moving toward a fixed control volume. And here the boundary of the system at time instant t, and here the system leaving the control volume at particular time instant. So that means I have a fixed control volume here. So it's just like I have a particular fixed control volume, and there is a system which is moving. It can come and overlap with the control volume, then again goes out. So this is how this moving system is behaving. So at time t, the system definitely coincides with the fixed control volume, as we have talked about it, because the system is going from these to that. So what we would try to make a connection that the system total derivative and their partial derivative, that means which is your Lagrangian description with that. So that brings to an important equation in any continuum mechanics, I would say. Obviously, here we are talking about fluid mechanics. So we would have so here the Reynolds transport theorem says that for any extensive property B and their corresponding intensive property beta, RKT states that the total derivative or the material derivative of that particular system, which is a partial derivative, their fluxes across the control surface. Obviously, the beta or B of the system, because the extensive property is B, which is the beta dm, depend on the time. So here, essentially what it tries to connect is that your Lagrangian description with your Eulerian description for an arbitrary volume of fluid. So what we can write is that if you look at the simple derivative, so here this is my total change of the B. So I'll write in terms of limiting variable over del t plus del t, and t. I'll do a little bit of algebra here. So I'll get these terms segregated, okay, and add this one and subtract the same thing. So if you collate the terms together, so what we can do is that this gives me the partial one, and this is the derivative due to the control surface. So what happens is that if you try to look at more from pictorially, this is at time t, the volume, and this is what happens in the, so this is what the change of B. This happens within that, and then it becomes like that. So that's the change with respect to the control surface. So one hand, you try to see the change of that intensive property with respect to time here, and then with respect to the surface. So the RTT provides you the rate of change of B of the system, which is the total derivative, then rate of change of B in the CV, and rate of flow of B through the control surface. So if you have a control volume, obviously this can be also be put for moving or deformable control volumes, but yeah, this is a very unique theorem, and using that, all your conservation laws can be defined in fluid mechanics. I mean, needless to mention here, this Reynolds transport theorem is applicable to solid mechanics also in continuum assumption, under the continuum assumption. So that's probably the primary key source for getting the equations for all these solid mechanics or fluid mechanics. Obviously, it starts with RTT, and then with certain assumptions, they bifurcates. Okay. If one has to say what is the difference between this and this, if let's say B equivalent to the mass. So you consider a control volume, which is just enclosing the fire extinguisher in service. So here, this is always decreasing if that whole thing is on. But if I look at the total derivative of the system with time, then it's always zero. That is the difference between. So one is that the control volume I can have along this fire extinguisher in terms of total derivative, this is zero. But whereas if it is open, then it's always decreasing, having a decreased mass. So that becomes negative. So now we can find out the conservation of mass or mass conservation equation in integral form. So what it says that conservation of mass is that dB system by, so this is what we get from the RTT. And here capital B is M and beta is 1. If you put it back, this is the dN. So the mass the system is not changing. So this gives me this equation. So this is in an integral form. I have mass conservation equation. Okay. Once I write that, I can now simplify that constant density or mostly non-variable density incompressible flow. So here the CV doesn't change essentially, so this is 0. Similarly, for steady flow, where I get this because the CV doesn't change. These are, I mean, this is my original mass conservation equation, and these are my situations where we try to see whether the flow is. Now, the important thing that we kind of touched upon while talking about what is fluid or for the definition of the fluid and things like that, the Knudsen number in the continuum scale. So continuum hypothesis is applicable when this length scale is very, very high than molecular length scale, that is mean Flipper. So you can see the range, this is what we are dealing with it, which is a very low Knudsen number. And then there is a range which is called the slip flow regime. There is transition regime. This is free molecular regime. So Knudsen number is defined like an lambda by L. So here for fluid, this is less than 1, very, very much small. So the continuum hypothesis that we are dealing with all the continuum scale phenomena and all these things, our Knudsen number is absolutely very small. So as the Knudsen number increases, so in some point of time it could be order of 1. That means the lambda is somehow equivalent to the L. That means the mean free path and the molecular length scale. I mean, essentially the mean free path and the actually the characteristics length scale are of the same order. The kind of going towards the transition regime and then goes to the mill. I mean, once it crosses, if it greater than 1, I mean, obviously, or 10 or so, such that it goes to a free molecular zone. So that's something one we are not talking about here. So now, if we try to summarize the things, one we have a Lagrangian definition, which is particle based. Another one is a Eulerian definition. Here we model the fluid as a bunch of particles, maybe many particles, and we track the particles. We track their instantaneous velocity, positions, and things like that. So you can derive their local accelerations. Here we talk about it's a many points in space. So fluid particles arrived at a point and they comes and goes out. So it's more like an individual particles are not tracked. Rather, we try to look at the fluid particle when it passes and they. Now Lagrangian description. This is a path line of the particle. That means the particle has actually traversed through these points. So this gives me path line of the particle. And then the particle position would be a vector. So I can find out from the initial position to where it is. Then it can give me the particle velocity, their acceleration. Okay. So in Lagrangian description, position of a particle is not an independent variable, is a function of independent variable time. Particles are identified based on the initial condition. Okay. If we look back the Eulerian description, so there is a point in space. This is obviously in continuum scale. The point is always occupied by some fluid particles, so we can find out the coordinate. Any property is defined space and time. The above property is the property of the occupiers, and the Eulerian description point coordinate and times are independent variables. So there is a difference. But whereas we can combine these two together, we have a path line of the particle, we have the particle position, we have the point coordinate. So we can say that this is the material derivative of that at a particular time, then this could be partial derivative of time and then respect to these vectors. So which essentially gives me back the equation that we have seen. Okay. So that means the Lagrangian and Eulerian, we can combine them together and get the integral form of conservation equation. Okay. So when we look at the Reynolds transport theorem, again going back to the system. So here we are now looking at the momentum conservation. For momentum conservation, what we look at it, we say that mu, b is mu and beta is u. Then if I put back in that RTT, so this is my RTT, and then we define b and beta, then I get this. So momentum conservation principle says that dmu by dt is the. So integral formulation of momentum conservation equation. So F equals to, this is the partial derivative, this is the convective derivative. So I have two forces to be balanced out. One is the surface force. So all forces which are acting on the control surface. So if I have a control volume like this, so this is a control surface. So the forces that is acting on this and the body forces. So if this is the one, so this is the AP, body forces, which could be gravity. And the surface forces are usually come from pressure, shear, interaction with the solid objects and this. Okay. So now if I write them together. So what I have is that surface force plus body force is this Lagrangian derivative and the convective derivative. So obviously in incompressible flow, we assume density is not very much. So we can write this. And in a non-deformable control volume and steady flow, we write this. So this term goes to 0. Steady incompressible flow, this again simplifies to this. So these are the different situations where you can simplify stuff like that. So pressure force always at the control surface, which is towards the control volume, is compressive. That means if we have some and pressure is acting like that, then this is behaving like a compressive force. Whereas if pressure is used like that, then it's a tensile force. There are some thumb rules of choice for control volume. Surface normal at control surface should be along or opposite to the flow direction. If we have uniform pressure distribution over a closed control surface, so eventually that leads to zero pressure force. Then the reference pressure simplifies the force calculation. So these are the example of different system where this is a hydraulic turbine versus Pelton wheels. So here you need to fix your reference system along the rotating frame of the system so that you try to find out the down equations or rather get the calculation done for that system. Now, what we're going to touch upon is that look at the momentum equation along a streamline. So if I have a tank like that and this is connected with the pipe, so if there is a streamline coming out, so along a streamline, we want to write which is known as Bernoulli's equation. So this is extensively useful for steady frictionless flows. This doesn't require, it is not essentially a differential, not integral formulation. Obviously, it can allows you to predict the real life situations fairly well. Okay. So how do we find out? So you assume a steady incompressible flow along a streamline. And then I have some pressure at this and then density, velocity. So I write the mass conservation. So BA, which is B plus BDA, momentum conservation, the pressure force, body force. So this phase is rho v square A, other case rho v square dB. So if simplifies, we get this. Okay. Now the pressure for surface, I mean the all surface forces, the pressure force at the surface, which are PA and P plus dP by 2 AP. So if you do that, that gets a body forces sin theta. So momentum conservation get me this. So which is essentially this. So from momentum conservation, if I take the differential of that, so that allows me to get this b square by 2 plus p by rho g z equals to 0, which is constant along a streamline. This is very much well-known equations or known as the Bernoulli's equation, which is applicable to steady incompressible frictionless flow. So this is very, very important to note, steady, incompressible and frictionless flow. Obviously, Bernoulli's equations, if you are interested enough, you can look at the textbook. Bernoulli's equation can be derived for more general situations such as unsteady, compressible, viscous flows as well. But yes, they might not look so simplified system, but it can be done. So now, if I look at that Bernoulli's equations here, one can comment that no real flow is strictly frictionless. But the Bernoulli's equation is still used in real flow to have an idea about the pressure. So what is the consideration here when the flow is away from the solid wall? You may sometimes be considered as a frictionless. Again, the flow under the special case known as irrotational flow, for example, if this is my solid one, and I'm talking about flow here, which is irrotational flows when it goes out from the solid one. So obviously, in those cases, B is constant and all these things. So if I write the Bernoulli's equation, then it comes with those assumptions like steady, frictionless, incompressible. But generally, frictional effects are very, very significant in narrow flow passages, diverging sections, weak region, near wall, separated flow. All these are situations where Bernoulli's equation should not be used because, I mean, obviously, one can use that by, I mean, it's a theoretical calculation and one can forcefully use that, but it might give you all kind of wrong calculations. So here we can see the flow past an airfoil. Stick lines are attached to the solid surface. Here the stick lines are slightly separated. So this is the zone which is called separated. For a, as soon as you, so here it is a zero angle of attack. Here you change the angle of attack. Here there is a wake behind the moving baseball. Here one can clearly figure out this particular case. You can apply Bernoulli's equation, but when we are just little away from the solid surface in case 2 and 3, we do have far away from the solid surfaces. So these locations you can still use, but not here. This is where you cannot use Bernoulli's equation. This is where you cannot use Bernoulli's equation. So someone or one has to be careful while using those Bernoulli's equations. We assume steady, slow, quasi incompressible frictionless flow. So here is a tank, and through which there is a tap connected to that or outlet through which this is coming out. So we can apply Bernoulli's equation and find out the velocity here. So we can apply the mass conservation. So here and here, then we can use the mass conservation. Obviously, it's an incompressible, so density doesn't change. If you can constant, you get this. Then you apply the Bernoulli's equation between 0.1 and 0.2, you get the V2. This is a simple example of Bernoulli's equations where you can find out these things easily. Here is another example. Here you are supposed to find out the effects at the flange where there is a water flow of 1.5 meter cube per minute. Again, the assumption is very important, steady, incompressible, frictionless flow. So the P2 would be atmospheric. So now across this, I'll write the mass conservation. So 0.1 you have A1 U1, here A2 U2, which is the Q. If I use Bernoulli's between 1 and 2, I'll get, because other terms like there is no elevation because they are at the same plane with the velocity difference. I have the pressure differences and the momentum balance. If I write, then Fx plus here they're having the pressure force and then connect with the change in momentum. We can find out the Fx from here. So one can see that you can easily apply two equations to this kind of situation. Now we move to the another conservation equation, which is the energy conservation equation, which write dE by dt q dot minus w. The Reynolds transport theorem says this, where E is the specific or unit energy or energy per unit mass, and rate of the work would be shaft work, shear, pressure, others. If I combine, then Q dot minus W is rate of change of energy and the convective transport of that. Now, if you have this kind of thing, here is the surface normal velocity, then I can find the elemental pressure here. I can find the displacement rate, then I can have W dot pressure at this control surface. If I put it back, then my energy equation becomes like this. So what it looks like that I'll have Q dot sapped here others and then changing. So if you have a steady flow, this goes to 0, then you get this energy. This E has internal energy, kinetic energy, and potential energy. And I can write in terms of enthalpy as well. So there's a different way one can write it down, and if you write that, and you can again put it back in the main equation, so you can get. So enthalpy is essentially my internal energy and P by rho. So P by rho plus internal energy. So again, steady non-dependent quantum volume, I can write change in H plus U square by 2 GZ this. So if there is no farm turbine they are involved, then the sap work is not there. So if there is no losses, then this is a steady flow energy equation that one can derive. So this can be used for steady flow energy system. So which one can write for isothermal adiabatic one inlet one exit system. So this is my internal energy which is constant, then adiabatic mass flow rate, then I write this equation system like this. So I can write that m dot p by rho z square minus losses. So these are the system one can apply. So if you extend that, then you can connect. This is the pressure head, this is the velocity head, this is the elevation head, this is the shaft torque, this is the head loss. So from here you can find out. So find out the power. So it can be easily applied to a system where your pumps and all these things are involved. Now you can look at this particular example where there is a kind of a dam through which there is a tunnel involved, and you can apply this equation and find the loss. So from head loss you can find out how much power is going to be used. So this is an example. So if you put it, so let's say how much available friction, and then if you the total power you can find out. Similarly, in this particular case, you can find out how much power is going to be. So that energy equation with the head loss one can apply and then find out. So connectivity between Bernoulli's equation and the energy equation is that Bernoulli equation is kind of applied along a streamline in a frictional flow where the energy equation, velocity, pressure are averaged over control surface. They look similar for adiabatic isothermal frictional flow with no work interaction, but in some cases they may be different. Okay, so if we try to recap what we have been talking about, that we have talked about this RTT, then if assume the control volume doesn't change over a time, that brings there, then now, so from RTT, you get your mass conservation, and then you get momentum conservations and all this thing. So using RTT, you can actually find out all these conservation equations like mass conservation, momentum, energy conservation equation. Obviously, one can, these are all written in integral form. Now, one can also write in the differential form, which is shown here, and that we'll discuss in further sessions. Okay.